talk about HLS, high-level synthesis, which is the means that Vivado provides to take C code and turn it into IPs, or intellectual properties, which is essentially libraries. That's really all they are, kind of like your DLLs in Windows, or your libraries in C, or your jar files in Java. So we're going to start with a few definitions. The first one is pipelining, and that's storing a computed value so the processor can move on to the next calculation. Think about it like a factory. If you have a production line, and at the end there's no place for it to go immediately, it has to wait for the truck that, let's say, takes 30 minutes. The whole line's going to be stopped for 30 minutes because they can't move the goods out so they can continue processing. Same thing with FPGAs. If you have a calculation and it's not ready to go, there are other pieces that make it not ready, that have to be finished before it can go on to the next step, and there's no pipelining, the calculation's going to have to wait. It's going to have to sit there until the other parts of the calculations are completed. With pipelining, you can put it into some kind of storage unit and move on to the next calculation. And that leads to two other very important concepts. Latency, which is how many clock cycles it takes to perform an operation, to perform a calculation from the time it starts. An initialization interval, which is how long it takes for a new new data to start being processed. So the total time to process, if you have n units to be processed, is n minus 1 times the initialization interval plus the latency. So let's say it can only accept data every 2 clock cycles. And you have 10 units of data. So you're going to it's going to be 9 times 2, which is 18, plus the latency, so it's going to take 20 clock cycles. And this is the example they give in the workshop PDF. If you can implement pipelining, so the initialization interval is only 1, because it can, while it's doing the first part of the other calculation, it can send it off and you don't have to wait. It'll reduce it to 11. So it reduces it basically by a factor of n. So that's when you're thinking about these designs, it's very important concepts to understand, and understand why pipeline is important. The main thing we're going to talk about today is synthesis, which is how you have code and turn it into a design that can then be implemented on a chip. Now in HLS, when they talk about taking a C design, or C++, and turning it into essentially Verilog or VHDL code that can then be implemented, turned into a package in an IP, which can then be used in Vivado and ultimately implemented on the chip. So it's one way of very efficiently implementing very efficiently creating reusable blocks, reusable objects. As you can see here, you have HLS, which you put into C++. You synthesize it into Verilog, and then you package it into an IP. This can also be done in Vivado. You can create your design, you can synthesize it, and of course in Vivado it creates the net list, the connections between the processing units to implement it on the chip. So this is how synthesis works. So what happens? So you've created these IPs, and we've seen this before, and we saw this last week with the pass-through. You have input ports. In that case, it was input from the camera. You have IPs that do various things. They may convert RPG, different types of signals to other types, etc. Then you have your processor, and that may send things out to other IPs, or may go, which may ultimately, I think this looks back, those are backwards. Anyway, I'm not going to worry about it. Which may, those are outputs. Which will in turn go out to, so you can have your buttons, and then you have your, you might have your blinking lights, or you may have your HDMI. The processing system is where, remember we saw the SDK, that's where your SDK code. So it's going to take input from the IP, from the ports. It's going to do something to it, or it may send things out like text to tell you what's going on, which we saw with the the menu items for the pass-through. And it can send them to other IP, it can send them to a GPIO port, it can send them to a terminal, etc. So this is how our IP is used once we create it. So what's the HLS process? First you create C or C++ code and test bench code. If you, coming from a Java programming background, I like to think of test bench code as you have your JUnit test, so you're going to write tests to test that your code works correctly. If it creates a calculation, the output is what you expect it to be. Then you're going to run C simulation, and that's going to verify that this test bench passes. It's going to say, yep, your C code, your C++ code matches what we expected. Then the next thing you're going to do is run this synthesis to create the VHDL or Verilog code. And after that, you're going to run what's called co-simulation. You're trying to verify that the design meets performance specifications, in particular things like latency and initialization interval. Once you're happy, and you can try different things, there are different directives you can give to it. If you have loops, you can tell it to unroll the loops. And you're basically trading off speed for landscape on the chip. So if you unroll a loop, you will use more of the chip, but it'll be faster. That's the kind of trade-off you're making. Finally, once you're happy and everything's running within your specifications, you're going to run export RTL. Export RTL is essentially going to create your IP, generate your IP. Your IP can then be imported into other designs. So now you have something that can be used elsewhere. And again, the whole purpose of this is reusability. If you have an algorithm which processes, let's say, video signals in a particular fashion, and you write it, and you're like, great, It's written, it's done, I know what it is. You don't have to, you can just pull that in next time and you already tested it. Okay, so now we're going to look at the process using Vivado HLS. And as you can see, this is actually based on Eclipse. So if you're familiar with Eclipse, this will be very comfortable for you. As you can see, this is basic C code. You're taking in this method, you have a float and an integer, and you perform you multiply by power. So, what we're going to do, the first thing you want to do, once you have your code, and let's also look at the test bench, because that's the other thing. This is again a program, and again this comes from Digilent, this is not mine. What it does is it runs a bunch of test iterations. It's going to calculate the result from the method above, and it's going to do a software calculation using a known method. So, the known method is the C-power method, and then it's going to print out the results. It's going to test, and if they don't match, then it indicates an error. If it doesn't, then it's going to just print out the numbers. That's how this testing is going to work. Very simple, very straightforward. So the first thing we want to do then, once we have our code in our test bench written, is we're going to, where is it? Run the C simulation. So that's going to run the test bench on the C code and verify that it's correct. And you can see we're going to launch the debugger, and I believe I do have some breakpoints that we'll see. So let's let it go. So it's starting, and it is now this is in the test program, and you can see it's getting its first value at test. And let's just run through it once. Where'd it go? Here we go. Again, this is, if you're familiar with Eclipse, it comes from Eclipse. So what it did is it calculated both numbers. And it's going to prepare to print it out. And because there was no problems, now it's going to get another test input. Where's our console? Here. So you can see the first, and we're gonna turn this off, I think, and just let this run until it gets it. I think I have a breakpoint in the actual. I turned the breakpoints off. So, just like in Eclipse, you can turn breakpoints off. It's that same little icon right here. And we're going to turn them on, and we're going to go. So now we're in the method. And so you can see if it is not appropriate, it's just gonna, if it's 0, it's just gonna pass it through. If it's this, that's the overflow case and an underflow case, so it's none of those, so it's gonna calculate our value and return it. And let me turn because we don't necessarily want to watch all of them. But you can see it does a bunch of these. And sine, exponent, the result, etc. So now we have a passing test. The next thing we're going to do here, now that we know that our code is correct, is the next thing we're going to worry about is performance. And that is where, let me find it. We should, I may be in the wrong view for that. Here, we can run the C synthesis. So, now here's the thing, you can have active multiple solutions, and that's a function of how it is set, what kind of directives you give it. For example, we have in here that's saying this whole function is always run inline. And that means you're not going to pass things down, it's going to be run flat, from what I've read in the definition. But you have various pragmas, and this is one, so what we're going to do is now run the synthesis on the active solution, and it's going to now create your VHDL or Verilog code. Now, one thing with pragmas that you can, again, the pragmas, as I mentioned before, and the directives you give it are a function of the trade-off of size versus speed. For example, as I said, if you unroll a loop, faster, more space. So we've run our synthesis, and we have, this is I think the error range, but you can see that we're in bounds. Our latency is 1, our interval is 1, everything is our utilization, how many lookup tables, how many flip-flops, I think that's what FF stands for, flip-flops, that it uses, and there's no problem there. It's not overwhelming the chip. It's a very simple program. I wouldn't expect it to. Now, when we run this on something more complex, like video processing, you would expect that you would be using more of the using 83 registers. We'd be using more of the resources of the FPGA. But right now, we're in good shape, not overtaxing, well within our bounds. The next thing we're going to run is co-simulation. Now again, the co-simulation is again another test to make sure that everything is within bounds. So it is running it again. And we're looking at latency and interval, and so it's doing its thing, and looks like it is done. Or is it? Okay. So this is our co-simulation report. Everything passed. And you can export this. So the interval, min, average, and max 2, latency 1. So it takes And that's apparently since we're doing the test in Verilog. Now that we know that we passed, we're within bounds of what we're expecting, we can actually export the RTL. This is what is going to make an IP module. So let's give it a name, display name. Let's call it test IP. And you can see, let's see where it puts it. So also you set this is setting the target device to RFPGA, and let's see, is it done? Okay, so now once you have your IP created, you want to bring it into your block design. In order to do that, one thing I didn't realize when I did it originally, in HLS you have, if you notice here, when you're looking at the synthesis report, it has a target device. This device must, for this solution, remember you can have multiple solutions, so let's say you want to target 10 devices, you create 10 solutions. But in order to set that, you have to go under solution settings, synthesis, and you see part selection. When you bring up part selection, you could target either specific processors, or you can target processors here or boards here. Now I targeted the Zybo Z720 because that's the board I have. Now what I could do is do something like this. Let's get out of here, and solution project, let's see, where do I add a solution? Okay, new solution. So let's say it's solution 2, and I want to target the other board I have, which is an RD a S730, I think it's the S7, it's the RD S750, Spartan 7. Just gonna look, make sure I have the right one. I believe it's a 50. So I click on that, and copy directives and constraints from solution 1, do finish, and then I could synthesize all the solutions. Already, actually what we want to do is, since we already have the one synthesized for solution 1, we're going to do solution 2. Synthesize that. What are we doing? Whoops, we're doing solution 1 again. What happened to solution 2? Here's solution 2. Well, we'll redo. So, solution 2, let's go back here and run C synthesis, select solution, and we'll add solution 2, and we'll do that. Now it should be doing solution 2. And this is how you make it compatible for the different boards. So now export RTL. And let's do that. Let's give it 2. And what this is going to do is it's going to create a zip file. And what you need to do if you want to bring it in, we'll go and let's see what it's doing here. It may be synthesizing, yeah, it's synthesizing solution 2. So anyway, that's how you handle multiple. And if you don't have the right boards, it's going to get frustrating. Now, when you go back to your Vivado, project, let's bring that up. And you're going to want to add, the first thing you may have to do, go into IP catalog, and yeah, I tried adding a few times. You have your user repository, and you can say add IP to repository. What you're going to do, I'm not going to actually add it, but you see, you don't want this here. Let's go up. There should be solution 1, implementation. Let's see what. It should be a IP, and then you'll see a zip file, and that's what you're gonna tell it. So once you have this, you may want to add it to your design. So let's go back to our design. Open block design here. It's already open. We simply add it like any IP, and we'll do test IP, and there it is. So you have your X, your N, your return. You have your clock, your reset, because remember things happen on clock. And your control, start, done, idle, ready. And there you go. You have your IP. So this is kind of how everything fits together with HLS. One of my goals for this week, because we are going to go over the HLS edge detection IP that they create in that workshop. However, as I mentioned previously, I had to bring in the Vivado project, the pass-through that we looked at last week. I had to bring that in as a, do not change anything. So right now, the one that's working, I can't add that IP in because it's not going to allow me to add anything. So I need to get it to, in order to demonstrate adding it in, I need to get a version of the pass-through working where I update everything and make it modifiable. So that is something I need to take a look at. But at any rate, that is the HLS and how that basically works, and how it relates to Verilog and VHDL, how it relates to to the Vivado tool, the HLS tool, and we even did how this fits in. Of course, if you're looking at this, the zinc, this is our zinc system, and you can see there are different inputs and outputs. Here is our processing system, and that's where you take the IP inputs, you do stuff to it. Anyway, so thank you very much, and hope this was informative, and see you next time.